classroom style podcasts. This one is on SHM and waves. And we're going to look at energy changes during simple harmonic motion. Syllabus statements wise, we have got free fill syllabus statements, assessment statements relating to SHM. We have to look at the interchange between kinetic energy and potential energy. We have three equations, and we also have to be able to solve problems both calculation using the equations and graphically. In terms of kinetic energy, this is the equation for velocity. Okay, so velocity equals the angular frequency multiplied by the square root of x0, which is the amplitude, the maximum displacement squared, minus the actual current displacement squared. That's the equation for kinetic energy, which you should be familiar with, and we can substitute in the equation the velocity into the velocity for the kinetic energy equation, and that is what we get. So that equation there describes the kinetic energy for any given displacement. Kinetic energy equals a half the mass, constant, omega squared, constant for a particular spring, amplitude squared, constant, minus x for displacement, which is our variable. Notice that the maximum kinetic energy occurs when x equals 0. When x equals 0 is equivalent to a displacement of 0. That's when the pendulum is straight down, or when the oscillator passes the 0 displacement point. So if we feed that into the equation, we have a maximum kinetic energy of a half m omega squared the amplitude squared. So that gives you the maximum kinetic energy. What about the total energy? Well, the total energy of a system is the kinetic energy plus the potential energy. But since this is a closed system, we have to have total, constant total energy. In other words, it starts off with potential energy, that gets converted to kinetic, gets converted back to potential again. In fact, let's have a look at that using the simulation here. So we have our bob over at one side. That's an angle of 35-ish degrees. And we press play, and we can see. Oh, there we go. Yep. So we can see that as the pendulum swings backwards and forwards, the green arrow is the velocity vector. We have the total energy, which is unchanged, but it's a trade between the potential energy and the kinetic energy. Run this a little bit slower. Then maximum KE there, 0 kinetic energy. Maximum KE. Maximum potential energy at the edge, 0 potential energy as it crosses the displacement line, back to maximum again. So here we can see how the two trade between each other. Going back to the presentation. So the kinetic energy plus the potential energy gives the total energy, and as we saw, at one point we have maximum kinetic energy and 0 potential energy, which we see from the I shouldn't have done the snazzy fade in. So there's the maximum kinetic energy equation, and that is the same as the total energy equation. So the total energy of the system is a half the mass of a bob, omega squared, amplitude squared. Potential energy, we take that same equation, total energy equals kinetic energy plus potential energy, rearrange it, potential energy equals total energy minus kinetic energy. There it is with the two terms which we've taken from our previous results, and that gives us a potential energy of a half m omega squared amplitude squared, which is the inverse of a total kinetic energy, as you would expect. As well as using the equations, we can look at this graphically. So the total energy against time is constant, as we've seen. The kinetic energy of time varies. Okay, with time it goes from a maximum to 0, to maximum to 0, to maximum to 0. And the potential energy graph is the same, just inverted. So the bottom two of these graphs added together will give you that constant flat total energy graph. And that's all there is to know about energy changes in simple harmonic motion. How do I shut this thing off?